Let us solve a couple of air conditioning problems. Let's start with a simple heating problem. As shown in the schematic here, moist air enters this tube at state 1, an air conditioning duct, and it's heated, let's say by an electrical heater or maybe by an external heating source. And the heated air comes out at state 2, and the following informations are supplied. Number 1, the volume flow rate is given to us at state 1, 100 meter cube per minute. Temperature at state 1 is given, and relative humidity is given. We know the final temperature, and the question is find the relative humidity phi2 and how much the rate of heat transfer in this problem to accomplish this air conditioning task. So let us first detect the process on the psychrometric chart. This is a schematic of the chart. So T1 is 10 degrees Celsius and phi is 90%. So probably the state 1 is somewhere around here. Of course, in a details chart, it will be nicer. This is just a schematic here. State 2 is somewhere at 40 degrees Celsius. So anywhere along this line is going to be state 2. Now what's going on here? As we heat the air, notice that at state 1 and state 2, what remains constant? As you recall, omega is given by mass flow rate of vapor divided by mass flow rate of dry air. So at state 1, it's omega 1. At state 2, if you think about it, at state 2, omega, the mass flow rate of vapor or air, neither is changing because the amount of air that enters every second cannot be different at state 1 and 2. The amount of vapor that enters at state 1 must be same as amount of vapor that exits at state 2 because we are not adding or subtracting any water molecules. So even though we are heating the system, mass conservation will tell you that omega 1 must be equals omega 2. We know this axis is specific humidity, which is omega. So therefore, we'll horizontally move until we hit state 2 at 40 degrees Celsius. So the task becomes very simple. What is phi2? We can simply pick up phi2 from the chart. And what is q dot E? And for that, we have to solve energy equation. So let's first find phi2 from the chart. We start the actual chart, which is table F1, and state 1, let's locate state 1 first, is 10 degrees Celsius, and what is the relative humidity? 90%. So 90% line is somewhere here, and 10 degrees Celsius is somewhere there. So this is my state 1. Oops. 10 degree and 90%. Okay, I'm just approximate here, approximately locating the state. And then we move horizontally until we hit 40% line. So the 40% line looks like somewhere here. So this is my state 1, this is state 2. As you can see, the relative humidity line, the one that passes here, is about 10%. So I will venture that the answer is 10%. From the psychrometric chart. Let's also pick up the enthalpies. Look, notice this is the enthalpy line, the enthalpy scale. And enthalpy, as you go here, the state 1 is somewhere here, and state 2 crosses somewhere there. So it's about 29 to 60. So from 29, the enthalpy goes to 60. Sorry. Okay. So let's pick up these numbers from here. So the answers we are coming up with, phi2 equals 10%, and H1 equals 29, and H2 equal 60 kilojoule per kg of dry air. Kilojoule per kg of dry air. So we have already solved what is phi. Now let's solve for solve the energy equation to find Q dot. So we know the energy equation is steady state, dE dt goes to 0, is how much energy is entering through moist air. The answer is this, where enthalpy is picked up from the psychrometric chart, and this is the dry air flowing in. The energy that is carried by the flow at the exit is given by this. We have already found H1 and H2, but we need to find m dot A. M dot A doesn't change across the system. So what is m dot A? If we know the volume flow rate, and if we divide by the specific volume at state 1, then we can figure out the mass flow rate. So, okay, so we need V1, specific volume, at state 1 to find the mass flow rate. V1 dot is already known, 100 meter cube, which is 100 divided by 60 divided by, let's go back to here, and state 1, remember 10 degree and 90% relative 90%. This was our state here. And the specific volume, if you look at, specific volume 0.82, 0.80, this is about 0.81. So if I just approximately take this value to be 0.81, what we end up with, 0.81, so many kg per second, so many kg of dry air per second. So therefore the energy equation is what? This is the energy that goes in by mass, comes out by mass, plus Q dot minus W dot external. So there is no external work involved in this problem. So therefore Q dot, which is given by m dot of air times H2 minus H1, which is 100 divided by 60, 0.81. And H2, if you recall, we found what is H2 to be? 60 and 29. 60 minus 29, and that comes to about 63.8 kilowatt. How do you get kilowatt here? This is kg per second, kg of dry air per second, and this is what? Kilojoule per kg of dry air. So as you can see, they get cancelled. We get kilojoule per second, or kilowatt. In this diagram, in this schematic, we show an air conditioning process which is known as cooling with dehumidification. Cooling, of course, is obvious. We are taking heat out, Q dot out, from a stream of moist air flowing through this duct. But dehumidification means the air is cooled below its dew point temperature, so that water droplets are condensing out, and the condensate is removed at state 3. So the information supplied are the mass flow rate of dry air is given, 2 kg per second. Of course, if the volume flow rate were given, we could have found the mass flow rate of dry air by dividing by specific volume. Temperature and relative humidity is given at state 1. Everything is known at state 1. At state 2, the temperature is given 10 degrees Celsius. The first question is, what is phi? And second is, what is the rate of heat out? What is the rate of heat transfer? Okay, first let's plot this on the psychrometric chart. So obviously state 1, which is at 40 degrees Celsius and 40%, will somewhat look like here. In fact, it's 40 line right here. This is our state 1. So what are we doing here? We are cooling the air. So we know when we start cooling, omega doesn't change. Look right here, as the air is passing from this point to this point to this point, the mass of vapor and mass of air, their ratio doesn't change, but the temperature will keep dropping because you're cooling. The cooling coils, let's say they start from here. So as a result, we'll move to the left, just like heating, simple heating. This is called simple cooling. But at some point, we'll hit the saturation line. Remember, This is our phi equals 100% line. So the air is now saturated, and what will happen if I cool any further? Moisture will drop out. So of course, once the air is saturated, it will always remain saturated. The further you cool, it will then, phi will be always 100%, but we're cooling, so the temperature is going down, down, down until the temperature reaches 10 degree. So my final state will be somewhere on this 10 degree Celsius line. Remember, this is temperature in degrees Celsius, or dry bulb temperature. So the final state is somewhere here, and phi is 100%, so this will be my state 2. So we found the answer for state 2 already, phi. The next question is find q dot out. Also, the other question could be find what is m dot 3. That could be another good question. In other words, how much water is coming out as condensate. As you can see from here, obviously state 2 has a smaller omega. You can go see here, this will be the omega at state 2, this is omega at state 1, and the difference between these two omegas must be accounted for by the amount of water vapor that is condensing out, and that will come out of the mass conservation equation. So let's find omega at state 2. The legit question to ask will be, what is enthalpy at state 1, what is omega at state 1, and omega 2 at state 2, and enthalpy at state 2, because we'll need them for mass and energy balance equation. We can go to the psychrometric chart and pick up those values. Okay, so we go to the psychrometric chart, which is on this diagram, and spot our state 1, which is at 40 degrees Celsius, and we keep going up where it is the 40 degrees Celsius line, relative humidity of 40%. Oops, this is not 40%. 40 degree and 40 degrees Celsius. So it's somewhere, what is 40% relative humidity line? Somewhere here. So I would say venture that it is, let's say, somewhere here. Actually pretty close to 90. Where the value of enthalpy reaches 90, it seems like. So I'm just picking it there. So this is my state 1, and state 2 is what, 10 degrees Celsius and saturated. So somewhere, it looks like somewhere there approximately. So this is my state 2, this is state 1. So let's pick up the values. Omega 1 is close to, look at the omega values. It comes to approximately, I would say, about 19. What would be that value? Well, I'll say it's between 18 and 20, so it's approximately 19. So let's pick up 19. Notice omega values are in here. Humidity ratio is given here. Oops. This is the omega axis, the omega numbers. And the dew point temperatures are outside. And the vapor pressure is over here. So the omega values are all inside here. So omega 2 would be approximately, if you go in this direction, I mean, I'll say 9 or 8. So I'll pick the omega value here to be 9 and 19. And the enthalpies are picked up from here. You can see 30 approximately. Of course, you should use a ruler to find these numbers more accurately. So 90 and 30. So I'm picking up these values here, and I'll go back to the PowerPoint and write down these numbers. So omega 1 we wrote down is about 19 gram per kg of dry air. That was the unit, gram of H2O. And enthalpy at 1 was about 90. Let me not write the units to save time. And about 9, I'll say 9, and H2 was found to be 30. So So therefore, if we go now and talk about the mass conservation equation, and we can very quickly figure out how much exactly. So recall, this is our diagram. This is state 1, 3 where water is living, and this is state 2 where moist air is living, right? So if I do a water balance, what do I get? M dot air that is moving in here, omega 1, that's how much water vapor mass is moving in, right? By definition of omega. That must be equals m dot air times omega 2, the amount of vapor that is living here, plus m dot of water at state 3. This is the condensate that's leaving the system because we are cooling. So therefore, our goal is to find the mass flow rate of water at state 3. M dot of water at state 3 is given by m dot of air, omega 1 minus omega 2. And if we substitute the values, 2 kg of water every second, and omega 1 is about 19, and omega 2 is 9, so many kg per second. Wait a minute. These are so many gram per second, because if you look at the unit of omega, this is kg of dry air per second, and unit of omega equals the gram of H2O divided by kg of dry air. Omega is multiplied by 1000, converted into gram, because water vapor is so little. So the answer here is 20 gram per second, which is 20 times 60 by 1000, so many kg per minute, if you want to express it in kg per minute, or kg per second will be 0.02 kg per second. Okay, that's the water vapor flow rate. How about the energy balance equation? Again, the energy balance equation, keep this diagram in your mind, and I'm just writing the energy equation from the fundamental concepts of how the energy is transported. At state 1, this is H1 times m dot A is the energy that is carried by the flow of moist air, and then moist air exiting will carry out this much amount of energy. The water that leaves, that also transports energy out. M dot water at 3 times enthalpy of water at 3 plus Q dot minus W dot external. So this is my energy equation. Steady state, this is always 0, and there is no heat, there is no external work transfer here. So therefore Q dot is given by m dot A. I'm switching side, so it will be H2 minus H1 plus m dot W3 HW dot 3. Okay, so if we substitute the values we already got, m dot A was given to us 2 kg per second, and we evaluated H2 to be 30 and H1 to be 90. M dot of water we calculate to be about 20 gram, which means 20 by 1000, so many kg per second. And what should be the enthalpy of liquid water? Well, the enthalpy of liquid water, notice that this term, the mass flow rate of water is so little compared to that of air, that you can see that no matter what the enthalpy is, the energy carried by the liquid water would be really small, because the amount of water is not so much. So to calculate enthalpy, even if we do approximately, that's very good. In psychrometry, it's always assumed that the temperature at 3 is same as temperature at 2, because as the water droplets falls here from the cooling coils, the air is kind of cooled, as well as the water is also cold. And this is a pretty good assumption to say temperature 3 equals temperature 2. You don't have to guess it. Generally, in a given problem, it will be given to you that assume temperature 3 is same as temperature 2. Also, you can assume that to find enthalpy at a given temperature, you know that enthalpy depends on, enthalpy is U plus PV, and for a liquid, you know U is a function of temperature alone. So enthalpy, strictly speaking, depends on pressure, but generally if you find enthalpy of liquid water at very high pressure, say in a pump, you think of this term. Otherwise, think the specific volume of water is so small that the contribution of this term is negligible. So enthalpy can be found from enthalpy of F point at a given temperature if the pressure is not tremendously different. So this is a simple model for finding enthalpy. Going back here, so enthalpy of water will be enthalpy saturated water at temperature at T2, which is 10 degree Celsius. So we can go and pick up, so this is minus 60 plus this is 0.02. Enthalpy at 10 degrees Celsius, if we quickly go find property tables, let's go for the saturation temperature table. In the saturation temperature table, if we look for 10 degrees Celsius, the enthalpy values HF is given as 42. So again, 10 degrees Celsius, enthalpy HF, saturated liquid is 42. Of course, to find exactly, if to add times pressure times specific volume, look at how small is specific volume. So barely this number will change. So it's 42. Going back, we substitute 42 here, and that gives us approximately, I would say, minus 119 kilowatt.